Dave Sebastian, and it's very nice to see you all. And today we have a packed program, and I will just show the topics now. And these are the topics we'll be covering. And the first section is about forces, and the second section is about pumps. And as always, this is our contact email address. So if at a later point in time, you would like to have the material that I use today, please send an email to this email address. We have a packed program, and it's unlikely that I'll be able to cover all the topics. And that is why I'm saying if you would like to have the information after the webinar, we can send them to you. I will cover as much as I can today. And the first thing I'd like to say about forces is that there is no rigid rule about how you calculate forces or how you define forces. It is entirely up to you. And you have to work with the PIPENET user will have to work in conjunction with the pipe stress engineer to decide what forces you would like to calculate. And PIPENET is very, very flexible when it comes to defining the forces. And the forces are defined by what are called control volumes. And control volumes can have several components in them. And the boundaries of the control volumes are called control surfaces. And we'll talk a little bit about them in a few minutes. That's the first thing. And the second thing I'd like to say is that when it comes to, there is a fundamental difference between flow analysis and pipe stress analysis. In flow analysis, we must always look at the global network. So any part of the network which is connected to the source of pressure surge or whatever you're looking at must be considered. Whereas pipe stress analysis is a local analysis. Usually it's from anchor to anchor, but you can do this stress calculations or reaction forces and so on as you like. And that is why it's very important for the pipe stress engineer to work in conjunction with the person doing the flow analysis. You have to work together as a team, and the load cases can be considered separately. And PIPENET is designed in such a way that the network doesn't have to change in order to perform the load case analysis, because the forces can be extracted as you wish. And this is a very, very fundamental point. And you will see this again and again as to why it is very important to do that. And why PIPENET, the flexibility of PIPENET in calculating forces is of fundamental importance. And of course, I mustn't forget to say that pipes do not get damaged only because of high pressure. They typically also get damaged because of forces. So that is why calculating the forces is actually a very, very important aspect of surge analysis. Okay, let's look at the first topic. That's the boundaries of control volumes. Now, boundaries of control volumes, it doesn't mean that you would necessarily put a control surface or the terminate of control volume at these points. There may be other points at which you may want to terminate the control volume, but these are items where it's essential to have a control surface. Why? Because the force doesn't transfer past this point. For example, if you have an expansion joint with no tie rods, then the forces cannot go past it. And if you have a blank flange, there is no way the force is actually going to go past the flange, because that's the end of your system. Or if you have a change in direction, and the force can only act on this item. It cannot get transferred to the other side of this elbow. Or if you have a flexible pipe to which you have a connection, then the force cannot go past it. So the termination point, or the break point, or the control surface, or whatever you want to call it, it's essential that it doesn't go past any of these items. Okay, that's a fundamental point. And that is what I mean by saying, when is it essential to have an endpoint of a control volume? And that's the first thing that you've got to understand. And then we consider simple and complex forces. What do they mean? This is the network I'll be considering throughout the presentation. It's an elbow pair, and there'll be other examples we look at, but this is the network that we'll consider throughout the presentation. It's because it's very, very simple, and it's easy to explain the principles of forces with such a simple system. And you can see, I mentioned that this elbow will have two components in the force, and that will be even in the steady state. Even in the steady state, that will experience a force, and you have F1x, F1y, and the vector sum of those two components. And of course, this could be in 3 dimensions as well. It's easier to see this as being on the XY plane. And this elbow also has an X component and a Y component and the vector sum of those two components. Forces such as F1x and F1y, which are in the direction of the pipe, they're called simple forces. Essentially, that's what a simple force means. Whereas F1, which is a vector, and it's in 3 dimensions, that is called a complex force. And those of you who have at least some familiarity with pipe stress analysis will know that we actually work with unbalanced forces in pipes, in straight pipe sections for pipe stress analysis. So when it comes to pipe stress analysis and reaction forces on pipe supports and so on, we will only use the simple force. The complex forces are not very often used, and for today's presentation, I will only consider simple forces because that is what you'll be using almost exclusively. And, okay, so let's have a look. Is the unbalanced force F1y minus the frictional forces, because what do we mean by the force? The force in PIPENET is the force that the fluid exerts on the pipe or some other item. It is not the force. We cannot consider the reaction forces from pipe supports and anchors and things like that in PIPENET. PIPENET only calculates the force that the fluid exerts on the pipe. And so sometimes this force can be very big. And that's because there is an external force from a pipe support or anchor, which is actually compensating for that. PIPENET cannot consider that because that is outside the pipe. It has nothing to do with the fluid force. We are only considering the fluid force. And the fluid force exerts 4 components. We're considering this pipe here, or this section of the pipe there. And don't forget that's F1y, F2y, that's the frictional force. We also have the static head force. So F1y minus frictional force, F2y minus the static head force. That is the unbalanced force. Don't forget friction, because the friction force acts on the pipe walls. So this is the unbalanced force. And simple force can only be used on straight sections of pipes, but it can have components within the control volume, such as valves, T-pieces, and so on. As long as the direction doesn't change, you can have a number of components within the control volume. And we'll see this later on. And it can only have 2 control surfaces by definition, because it's a straight section, and hence it can only have 2 endpoints to the control volume. A complex force is a force with 3 components. It's like the vector force F1 above. It's used for local stress analysis by finite element programs. It's not used by pipe stress programs. And it can be used for components other than pipes. And, for example, if you want to have the force on a valve, you may want to use a complex force. It can have more than 2 control surfaces. For example, if you want to calculate the force on a T-piece, it'll have 3 control surfaces, and it'll be a complex force because there's a change in the direction in a T-piece. If a T-piece is, of course, part of a straight pipe section, then that is not the case. But I'm talking about the T-piece taken on its own. And we calculate the force on that. That is a complex force. So let's consider the same pipe, and the complex force will be at this elbow, whereas the simple force will be the unbalanced force on that pipe. So let's go and open the data file. See, that's the data file, or the schematic of the data file we're considering. That's 50 meters, another 50 meters, 400 meters. The diameter it's not actually that important. It's 100. I believe it's 100 all the way through. And the pressure here is 0. The pressure there is 10 bar gauge. Because, of course, there's no pump or anything, so we need a pressure difference for the flow to happen. And this valve, as you know, it starts to close at 5 seconds. It's at 5 seconds, it's fully open. at 8 seconds is fully closed, and hence it takes 3 seconds to close. Let's go and have a quick look to see how I've defined the force. See that it's simple. See that it's by default, it goes to simple, and it's on pipe 1. If we show the labels and increase the font size, one, 2, and that of course is 2 as well. So let's go back to forces. See, the simple force is between the inlet and the outlet of the pipe. And we have the options of rigid at the endpoints of that control surface. If you remember, I said that for a simple force, you can only have 2 control surfaces, and these are the 2 control surfaces, and they're both on pipe 1. We look at the complex force. See, the complex force starts from here and there. So that's the way you define the complex force, because it's partly on pipe 1 and partly on pipe 2. So let's run it. By the way, I must mention that when you generate forces, you have to ask for them through results graphics, because we cannot simply right-click because a force is not a component. That's why you've got to ask for the graphical results here. Simple force. Now, it's a relatively small force, but it's very, very typical. And the complex force is defined here. We can have a look at that. Let me remove that for simplicity. I have a X component. You also have a Y component. They almost coincide. Why? Because they're almost at the same point. So the force acting that way is numerically equal to the force acting in that direction. That's one thing I'd like to mention here. You can see that they're both positive, but a positive force means something quite different when it's a simple force or a complex force. It's obvious when I talk about it. A simple force will be positive if it's in the same direction as the direction of the pipe. See, that's the direction of the pipe. So if the force is in the same direction as the pipe, it'll be positive. And if it's in the opposite direction, it'll become negative. Whereas a positive force for a complex force is different. It depends on the coordinate system you're using. And obviously, typically, that's plus X, and that's plus Y. And that's what we're seeing here. That's why they're numerically actually equal. You can see that there'll be a very, very small difference. We use, they're not exactly the same. They're slightly different because there's a small friction loss in that section. While we're here, we can also show you, we can zoom in as we like. I mean, we can use this to zoom in. Or we can use this. So you can zoom in that way as well in the graphs. So this shows the difference between simple and complex forces. I will not talk about complex forces anymore. I will only focus on simple forces from now on. But do remember that this is the difference. So let's go on to the next topic, which is forces in steady state. Let me close these documents. Okay. It's the same system I'm considering. And, we do not typically talk about forces in steady state. We only talk about forces in the dynamic case. In the steady state case, we say that as long as the pressure is below the allowable pressure, we're fine. And, that is because, for this reason, in steady state, there is no unbalanced force, or at least what I mean by that is the unbalanced force is equal to 0, because all the forces exactly cancel each other. And as before, the fluid is the static head, or the force due to static head. So we can see if that's true by doing some calculations in PIPENET. Let's go to PIPENET and open the data file again. Oops, I just had it. It's the same network. I'm just changing the boundary conditions. That is 0 as before. That is 10 as before. But this valve remains open. That's what we mean by steady state. That's nothing is changing. But the force, of course, is defined as before. We only have one force. From now on, as I said, we'll only consider the simple force. The interior point of 50 to 100. Why am I defining the force like that? Because that is the force in this section. Now, there's a very key point that I would like to mention here, but it's we'll see a little bit this in a little bit more detail. The definition of a force in a pipe like this is very, very simple. You do not necessarily need to have a node in order to be able to calculate the force. You can define the force, leave the pipe in this way and calculate the force on that section by defining the control volume appropriately. And that is what we're doing here. See, we're saying the control volume is the interior point. One is 50 and the other point is 100. We'll see a little bit more about this in just a minute. But this is only to show you that in steady state, the force is equal to 0. So let's do the calculation. Go to the graph. Force F1, because it's a simple force, there's only one component. Don't forget, this is always in the direction of pipe. And you might wonder, why is it that we don't consider 3 dimensions? That's because typically you will be using this in a pipe stress program, and the pipe stress program will know the 3-dimensional geometry of that pipe. We don't need to know that in PIPENET. Okay, that's a key point. See, is identically 0. As you know, if you hover over any point in the graph, you'll get 2 values. The first value is the number at a time, and the second value is the number representing the actual y variable. In this case, it's a simple force. So simple force is identically 0 all the way through. So this is what I was saying. In steady state, the unbalanced force is 0, and that is why in steady state we do not consider forces. We only consider the pressure and make sure that the pressure is below the allowable pressure. Okay, let's go on to the dynamic cases now. The valve was initially, no, it's better to go here. I'll keep closing those documents because otherwise we'll get a large number of documents. So this valve is closing, okay? And that creates a pressure pulse. And I will assume, just for argument's sake, that this pressure pulse is a very, very narrow spike. And initially, the spike will happen here, and that will move back along the pipe at the wave speed, and it will reflect from that point and come back. And the pressure wave will, or the pulse, will be keeping on moving back and forth between the inlet and the outlet of this pipe. And that is a very key point. And that's the reason why we get unbalanced forces. We'll just see that in just 1 second. But initially, when the pulse, because it's a very narrow spike, when it forms here, it doesn't change the unbalanced force here, because that is still 0, because this has not had any effect as yet on the pressure and the flow rate at these 2 points. And that's because I'm assuming it's a very, very narrow spike. So we are considering a step function for the valve closure, and that's a result, and we'll see that in just 1 second. It's the same network, 10, 0. The valve closure pattern is different. I'm using a step function. What this means is the valve remains at 1, in other words, fully open until 5 seconds, because at 5 seconds, I'm saying that it's changing its position from 1 to 0. So it's an instantaneous valve closure. That's what I'm considering here. And do remember that the closure takes place at 5 seconds. See, it takes longer because I've asked for the output for the pipe as well. And, and because the pipe is subdivided into grids, it takes much longer to output. So when you're actually running PIPENET, be careful about asking for results for pipes, because PIPENET will save the results at all the grid points along the pipe. Because as you know, a pipe, for dynamic analysis, is divided into segments. Okay. Show the valve position, instantaneous closure. So you can see the force remains 0. This is the point I was making, because the pressure pulse takes time to get to the input. If you have a look at it using the magnifying glass, you can see the difference. The other interesting thing about this is there are 2 spikes here. That takes a little bit of explanation, but I will not explain it right now, because it's actually the time at which the pressure reaches the 2 elbows. And that's the reason why we've got this double spike. I mean, you can see it more clearly if I zoom in. So you can see these 2 spikes. So that is what I mean by saying at the time the valve finishes closing, in this case, this instantaneous closure, you still won't get any unbalanced force until the pulse actually reaches that point. Now where things start getting more interesting. Let's close this. Valve closure unbalanced. See now, the pressure wave travels back at the wave speed. See here, PIPENET shows you the wave speed here. So the pulse travels at this speed from the valve to that second elbow. And that's what we're considering here. So when the pulse reaches that point, this component of the force becomes big. We're assuming that it's a short spike, the value of the pressure surge is significant, in which case that component becomes large. Why? Because that component is actually equal to the pressure times the area of cross-section of the interior of the pipe plus the mass times the velocity. And so that is high because the pressure surge increases the pressure, so that component. But the pressure surge, because it's a very short spike, it has not reached that elbow. So now this is where the problems start, but because now we've got a big unbalanced force. See, this is no longer equal to 0. In fact, you could say that F2y from here, which is equal to that, I'm just taking it to the other side, it's considerably bigger than that term. So the pressure surge is considered to be a spike. So let's go back to PIPENET and have a look. See, this again is F1. Now, I'm considering the valve to take a more realistic time to close. At 5 seconds fully open, at 8 it's fully closed. And so it takes 3 seconds to close. And I want to calculate F1. And my supposition is initially this will be a large value. And that is, this point is about 100 meters from the inlet of the pipe. But of course, don't forget, we're calculating the unbalanced force. So it involves both of these elements. See, initially, let's zoom in. See, this is it's approximately 5.3. That's force. It starts increasing approximately at 5.3. You know, what I said was that force will start to increase when the pressure surge reaches that elbow. So if you look at the wave speed, let's say it's 1380, and the pipe length is 400. So if it's 400 divided by 1380, it's about 0.3 seconds approximately. See, that's what we're seeing. So the force starts to increase when the pressure surge reaches that point. See, because we're closing the valve in a finite duration, it's not a short spike anymore. So it will begin to increase and then start, reaching a high value, as we saw. So that is what's happening in the first step. Then we'll consider what happens when it reaches the other elbow. See, now the position reverses when the pressure spike reaches the other elbow. That component becomes quite big, and that goes back to a smaller value. As I said, I'm considering this a little bit hypothetically in an extreme case. It will not be starkly like this. It doesn't shift from elbow to elbow quite that way because it's a wave front of the pressure. So this will not go back to a really tiny value, and that will go to a very large value. I'm just showing this for explanation purposes. See now, F1y, if I move these to the other side, is much greater than the other terms added together. That's what I would expect to see. We'll just see that in just one moment. Go back to PIPENET. And you just check the definition of the force. See, it's again, the definition of the force is the same because we're considering the unbalanced force on that pipe. What we want to consider is the value of the force at different points in time. Let's consider, let's say, between 7 and 10, let's say. So, 7. So you can see the force is now negative. And what's that mean? Why is it negative? It's quite clear, because the force is acting that way. The unbalanced force, that's what we saw. And that is in the opposite direction to the direction of pipe. Don't forget, it's the unbalanced force in that pipe section. And that is acting that way, and it's in the opposite direction to the direction of the pipe. And that is why the force became negative. In case you missed it, I'll go back to it. So I did. I zoomed in between 4 and 7. I'm sorry, it's not 4 and 7. I have to do it again. It's between 7 and 10. See, it's negative. You can just about see the negative. 0, and it becomes negative. Well, if you like, I can show you all these interesting things that you may not be aware of. So I can draw the 0 line. So it doesn't show that for some reason. Maybe I cannot display the forces. Anyway, there's something other. Maybe the limit lines are only available for other other variables, not forces. Okay, but it's clear that this is negative. It's because it's in the direction opposite to the direction of the pipe. So let's go to the next topic. Now, one of the things I said earlier on was you can calculate the force without inserting additional nodes, and that is the typical way of working. What's actually mean without inserting additional, and how does PIPENET do that? Because a pipe is subdivided into grid points, and you can calculate the unbalanced force if it knows the pressures and the flow rates at these two elbows. And in order to calculate, because it knows the solutions at the grid points, in order to calculate the pressure and flow rate at this elbow, it has to do a little bit of interpolation between the grid points which are adjacent to it. And it's the same here. So if you do not insert additional nodes, that is what we're doing. We're doing some interpolation. What are the advantages of not inserting nodes? The network does not change between load cases. See, if you inserted nodes, that means that you either know the load cases you want to consider before you set up the network, or you change the network every time you want to consider a load case. And if you did that, and if you have 100 load cases, you'd have to create 100 networks, because you'll be inserting nodes for every load case. So the great advantage of doing this is because the network doesn't change between the load cases. And usually the calculation it's a little bit faster because the pipe lengths are longer, and for that reason, the calculation is usually faster. The disadvantage, the interpolation necessarily leading to potential loss of accuracy. This is usually not a big problem because the time step we choose would be short enough to create nodes along this pipe. And so the nodes might be close enough. So the degree of interpolation you do may not be actually that great. And, and again, the linearity which we assume when we do the interpolation actually is not grossly inaccurate. So that's why I use the word potential loss of accuracy. Often, the level of loss in accuracy is quite small. And so these are the advantages and disadvantages of having grid points. And, we can have a look at, if you like, the case. This will take quite a long time to calculate, so I will not calculate with that. So I'll show you how to do the calculation with this. See, I've defined the calculation time step here. As I explained during the previous seminar, see, this will show you the number of grid points here. That's what this means. So let's look at the result. Another neat feature in PIPENET, as you know, you can open another data file. And let's not sure what the result is. Just give me 1 second. Maybe. There are so many files I'm creating that it's sometimes difficult to keep track. Let me just do this. Yeah. See, that's what I want to. Okay. As I said, I don't want to do the calculation again. So I have to open the results file. Unfortunately, I think that I removed the results, so that's why it's not here. But what I can tell you is that the difference is not actually that great. Yeah, I think I deleted the results file, unfortunately. And I don't want to calculate again because as you can see that the time step for calculation, and if I do the calculation, see, it's slower because we're asking for the results for the pipes, and that makes the calculation a little bit slow, so you can see. Okay, So you just take my word for it that the difference actually is not that great. What I will show you, the number of divisions is 362. In the previous case, it was 7. So even that kind of difference didn't make that much difference to the results or the false time history. So, to take this approach is relatively good. So let's go on to the next topic, which with inserting additional nodes. So here, we're physically inserting additional nodes, and because PIPENET will calculate the results of these 2 nodes, it does not need to do any interpolation. There are actually 2 differences. One is it doesn't have to do any interpolation. The other difference is the flow pattern itself will change a little bit because we've got 3 pipes instead of just 1 pipe to do the hydraulics. So the hydraulic results themselves will be potentially slightly different. What's the advantage? There's no interpolation, potentially leading to greater accuracy. And usually, there's not a great deal of difference. It has many disadvantages. One of them is that network changes between the load cases, potentially slower calculation. We also have to remember the pipe length in the control volume cannot be smaller than the wave speed times the time step. Okay, that is something you've got to remember as well. See, these are the results. With the time step, it's comparing the results, with and without the new nodes inserted. Okay. This is actually the comparison graph. Compare the forces with and without nodes, and that's the time step. And you can see that they're very, very similar. And the difference is more due to the fact that the dynamics of the system changes because the flow analysis itself produces slightly different results. But it's quite remarkable when you think that inserting those additional nodes and working without the additional nodes makes virtually no difference. Okay, that's the 2 cases. The next one I want to consider is these 2, and possibly that. And these are actually the main remaining 2 topics, and the other ones that I can go very quickly. What do I mean by multiple components? See, one of the beautiful things about PIPENET is the control volume can consider a multiplicity of components. The only thing is there must be no change in the direction. That's a key point. Because you can only have 2 control surfaces. So we can define the control volume in this way. Because we cannot have a change in direction, we do not consider the force in that direction. It's only the force along this section of pipe between these two elbows, and we define the control volume in this way. And that is the PIPENET network, because you can see that there's a control valve there, it's a pressure control valve, and there's another valve here, and also another valve here. So let's see. That's a network. The pressure here is 10, 0. That valve remains open constantly. That valve closes in 3 seconds. And this is a control valve. You know, we've already talked about a little bit about this previous time, but when we talk about control valves, we're going to have another webinar about control valves or control systems. And, you know, we'll discuss this in more detail at that time. And the PID controller parameters are here. So we'll see how this works. The way PIPENET works is actually quite beautiful. I will delete these forces and I will define the control volume. See, this pipe here is 30 meters long, and that length is 26. So this elbow here is 4 meters from the inlet of the pipe. See, that's the direction of the pipe. And this elbow is 10 meters from the input node of that pipe. So that's pipe 1, 2, and pipe 3. So how do I define this? Let's leave it as force 1, it doesn't matter. So this elbow is on pipe 1, is set an interior point, which is 4 meters from the input node of that pipe, because the length up to here, this elbow is 4 meters. Then there's pipe 3, and this elbow is 10 meters from the inlet of that pipe. So click on pipe 3. It gives a warning message. Are you sure that's what you want? And I say, yes, of course. That's what I want. This pipe. It's an interior point, and that's 10 meters from the input node of that pipe. See, there is this here. If I click on that, it'll give me a list of the components it's found. See, so you do not have to input all the components. You just input the endpoints, and PIPENET will work out where all the intermediate components are. See, it's beautiful, isn't it? It's very nice, very easy to do. And so PIPENET will infer the properties of all the components that are between those two elbows. So I can do the calculation. The rule is that it's got to be a straight section with no change in the direction. Yeah, if you remember, I said to you, you have to choose to input, ask for the results for the pipe here. force, and we can see that that's actually quite a big force. Okay, so this is how we deal with a controlled volume with multiple components. You don't have to worry about what is inside the controlled volume. PIPENET will do all the work for you. The next topic is a very important one. When I say very important, all the topics I'm talking about are important, but this one is important because it's lack of clarity with some people about what this actually means. What are rigid and elastic joints? See, if you look at the force definition here, see there's elastic and rigid. What do they actually mean? See this one here, if you consider the unbalanced force along that pipe, is the difference between the force there and the force here. So you would define them as rigid joints at both ends. But here, see, it's a freestanding pipe here. It's not, there's no restraint or anything like that here. Then the unbalanced force is simply that component. There's nothing compensating or acting to balance the flow of the force in the other direction, because it's a free end of a pipe which is not restrained in any way. The pipe could, of course, be restrained here or there. But the fundamental point here is, as I said earlier, what PIPENET calculates is the force that the fluid exerts on the pipe. This is a fundamental point. It's the force that the fluid exerts on the pipe. The compensating force, or the force that's restraining the pipe, is not something that PIPENET can calculate, because, you know, the PIPENET could be supported here or there, or this could be connected to a tank. And PIPENET doesn't know where they are and what compensating force they're exerting. That's one point that, you know, causes people a great deal of concern sometimes, because it's very clear that here the unbalanced force is the difference between these two forces. Whereas here, the unbalanced force is simply that one component. So here, the unbalanced force would tend to be much higher than the unbalanced force here. And people sometimes worried about that, but you see, that's only because PIPENET cannot consider the restraining forces. There'll be other forces which are restraining the pipe from moving. Okay, always keep this in mind. We are only calculating the force that the fluid exerts on the pipe or the piping system. We are not considering the external forces, which could be due to a multitude of items which are restraining the pipe. You know, if it's a power station, it could be snubbers or something which are restraining the pipe. We cannot consider what force they're going to apply. We only consider the fluid, the force exerted by the fluid. So here, this is rigid and that's elastic. So please understand this point, that there is no force acting in this way. And that's useful if we want to find out how we're going to restrain this pipe. whatever we're using to restrain the pipe would depend only on the force acting in one direction. Okay, that's the difference between rigid and elastic joint. Let's open the data file for that. See, so I've got one network here, F1 and F2. F1 first. See, it's rigid and rigid. Why? We are assuming that there are no flexible connections or anything like that. It's simply a rigid pipe in between the two elbows. So we define the endpoints as rigid and rigid. F2, on the other hand, by the way, of course, the positions are all different. I'm not considering them. And it's rigid. And because it's freestanding, it is elastic at this end of the control volume. The control volume is like so. And at the end of the control volume on this side, it's elastic, which is what we had here. And so on. So let's do the calculation now. See, when we actually look at the force here, it'll be quite big. F1 will be relatively small. That's because, you know, the forces here on each of these elbows will not actually be significantly different from the, you know, the single component force we're talking about. It is just that because we're taking the difference, it looks small. Okay, that's the force. It's quite small, as you can see. That's the force. F2 is the force with an elastic joint, and you can see. You know, and also you can see it's negative because it's in the opposite direction to the direction of the pipe. Whereas the first non-balance force is positive because that is in the direction of the pipe. So that is significantly bigger than that. But the point remains that F1 is the difference between these two forces, whereas F2 is only the force acting on that. That is why this is quite a bit bigger than the other. It goes to minus 8,000, whereas this one here only has a maximum of 622. So, you know, so this is in the nature of things that it just means that we have to have an external restraining force which stops the pipe moving. Okay, so that's what that is. Let's take an example. See here, you can see an anchor. Don't forget that the force applied by the anchor is an external force. We cannot consider that because the force in the anchor, you know, the restraining force of the anchor depends on many things. and which have nothing to do with PIPENET. And we have an expansion joint here, and we're considering the unbalanced force in all these 6 sections. So don't forget that this is elastic, that's elastic. This is also elastic because there is an external force which we do not calculate. Okay. So let's open the data file. The network itself will look quite simple. This is the position where there is an expansion loop. In fact, if you don't want to, you don't even have to define that as a node. But there are, because as you know, in PIPENET, we can define the force with complete freedom. It's up to you to define the force, and it depends on what you want to do. So these are the 6 forces. We can have a look at a couple of them if you like. See, these are the 6 forces. We pick F3 at random. See, rigid and elastic. This F2 is rigid and rigid. So we do the calculation. We just plot a couple of them. I mean, we don't have to plot all of them. F2, F4. And you can see that F4 is actually quite a bit bigger than that, because I presume F4 has an elastic joint at one end. It just means that it tells us how to support the pipe. Okay, that's what that is. I'd like, as I said, I'd like to not go through all of them, because we'd be happy to send you the files for these, and and people who have already got PIPENET, we can also send you the data files I've been using today. The only topic I would like to very quickly cover is the Caesar interface. We have a document that actually, I'm not opening up PIPENET, I want to look at it here. See, the philosophy in PIPENET, we use the spray sprinkler module and the standard module for design, things like pipe sizing, pump selection. How does the system behave under many steady state scenarios? That's the design process, and we complete the model. And then how does the system behave under dynamic conditions is what the transient module is about, and you can export the model from PIPENET steady state modules to the transient module, and that of course generates the time history. We saw that graphically, but PIPENET also produces the time history as a text file, and that is what Caesar2 can read. Caesar2 is not the only Postgres program. There are other programs such as Road2 or Road2 from Germany, which is another very good program, and they do the stress analysis. I said to you that PIPENET generates the force time history as a text file, and this is an extract from the text file. That's the time, and that is the actual force. And this document shows what are the steps involved in importing the time history into Caesar 2. It's a very, very clear document. And these, here you're in Caesar, not in PIPENET. I cannot show Caesar because we don't have a license for Caesar. You end up with a dynamic load factor. And you get the results from Caesar to here. Okay? So that is how the Caesar interface works. Now that's the topic of forces. As I say, unfortunately, we will not have time to cover all the topics because I've said to you, there are a lot of topics here. And if you're a licensee of PIPENET, we'd be very happy to send you the data files. And we can also send you the other documents and you can read them up yourself. I've covered all the fundamental points in some detail today. So let's go on to pumps. That's the second big topic. And as you know, there are 3 pump types in PIPENET. There's a simple pump, the turbo pump. These are actually the oldest models in PIPENET. We've had simple pump and the turbo pump, for the last 25 years in PIPENET. And this is a more recent addition. And that's simply because it's a dynamic pump, but it needs less data than the turbo pump. So the inertial pump, and there are 2 modes in which you can operate the inertial pump, pump trip, and pump startup. Because for pump trip, you will not need the torque curve because you're assuming that the torque that's rotating the pump is essentially becomes 0. So, we don't need this. Whereas for when the pump starts up, we will need the torque curve. That's why the inertial pump can work 2 different modes. And sorry, that's a birthday of a friend of mine, and that's showing up. So these are the 6 cases. And once again, I do not know if I'll have time to go through all of them, but I will go through definitely all the essential points. Simple pump curve. Let's be done with it. Okay. Let me close this. Simple pump curve, what is it? It's basically the pump performance curve supplied by the pump vendors. And it is usually the pressure of the head against the flow rate at the design point. Normally, the design point is the best efficiency point. What do we mean by that? If you plot the efficiency against the flow rate, it'll have a peak, and that's called the best efficiency point. And usually, the pump curve is supplied at that point, but it could be supplied at any point. It doesn't matter. And PIPENET uses what are called the affinity laws to calculate the performance curve at other speeds, other RPMs. And the relationships are shown here. You can also control the pump speed with an information node. But PIPENET itself cannot calculate the speed change in the pump because speed change of the pump depends on many things, like the moment of inertia, and the torque, and things like that. And PIPENET doesn't use the data. What are the advantages? The data is easy to get. The model is just the pump curve and the affinity laws. The affinity laws are built in. so you don't need to input them. But the pump curve, you must specify in the library. What are the disadvantages? Engineering generally, the rule we follow is the simplest model that's good enough for the purpose is the best option. That is what we always choose. And that's a great benefit of this model. The simple pump model is adequate from an engineering point of view for a large number of applications. So why go to the extent of inputting all the other data, which you don't need? Okay, that's the best advantage of the simple pump. The data is easy to get. The disadvantages: ignores the resistance of the impeller. What do I mean by that? If the pump is stopped, it doesn't mean the delta P across the impeller is zero, because if for some reason there is flow, the pump will actually act just like a turbine if the flow still keeps going through the pump, because the flow will rotate the impeller. And for these reasons, the impeller will actually give a resistance to flow. And the simple pump curve doesn't consider the resistance of the impeller. And it cannot, of course, calculate the speed by itself against time. It's something that you have to set up manually. So it's suitable when the pump works at a constant speed, or when pump speed is changed by a process controller, or even manually. It doesn't matter. If you have a variable speed pump and you want to change the speed of the pump, you can do it here. It's not unsuitable for abnormal cases like pump trip. I use the term abnormal. It's not really abnormal, because it could be, that the pump is manually stopped by an operator by switching it off. And this cannot model how the pump or the system may respond under those circumstances. You cannot model how the pump is going to start up. And you have to set this manually. Okay, so that's the disadvantage of the pump, and it summarizes where you could use them. So let's go and have a look. The pumps are running at a constant speed. The pump performance curve is defined here. The inlet pressure is 0. The outlet pressure is 0. You see it's 1,000 meters of 100 millimeter pipe. And the valve closes from 2 to 5 seconds, so it closes in 3 seconds. And of course, there is a non-return valve. Yeah, as you know, a non-return valve is like an instantaneous valve. As soon as the pressure reverses, it will close. Once again, it's a very, very simple model. If you click on that, there's no data. You simply say it's connected between nodes 2 and 5. That is it. See, that's the pressure at the inlet of the operating valve. And this is a very typical graph. So that is a simple pump. Let's go on to the turbo pump. The turbo pump is the most complex built-in pump. And it's based on the rated speed, rated torque, rated flow rate, rated head, and the moment of inertia, and the Suter curve. What is this rated? As I explained, usually it is the best efficiency point. At the moment of inertia, we know that, of course, is a constant value. And then the Suter curve. What is the Suter curve? See, it's defined in this way. The turbo pump has its name because it's a very comprehensive pump model which can work whether the flow rate is positive or it's negative, and the delta P is positive, and the delta P is negative. You know, it's a very classic situation where you see the, we can actually open the turbo pump case. See what happens. You click on that. See the turbo pump. Do you know what I mentioned to you? This is the best model to use, most accurate model to use if this is a trip of the pump. Or, you know, when I say trip, it could be because the operator switches off the pump. See, the problem is when the pump loses power, the pressure here typically would become less than the pressure there. Why? Because the fluid in this pipe is moving, and hence the pump is acting like a valve. You could say the pump is like a partially closed valve, and hence the pressure here could fall below the pressure there. And so you see the normal pump performance curve will not cover a point where the delta P is negative. That's a key point. But we have to cover that with a turbo pump. And they're called Suter curves. Basically, you can see that the flow rate divided by the rate of flow rate, which you've input, alpha, is the RPM divided by the rated RPM. Don't forget, these values can be negative or positive. And we can take the tan inverse, pi plus tan inverse of that is x. In the Suter curve, this is x. Let me zoom in. Okay. So that's x, and it goes from 0 to 2 pi. Because that goes from 0 to 2 pi. And these are all the cases. See, that's normal pumping because the head is positive, the flow rate is positive, the RPM is positive, and the torque is also positive. But in the pump trip condition, that x could become, so in this case, the x lies between these two values. That's the Suter curve values. So in this way, we can model all cases where there can be in any combination. The flow rate can be positive or negative. The head can be positive or negative. The RPM can be positive or negative. And the same with the torque. They can all have any values. And for example, you know, if the flow is backwards and the pump is rotating backwards, but the torque is positive, then the head, of course, is also positive. That's like a turbine. Okay, the head on is positive means the pressure here is higher than the pressure here, and that acts like a turbine. So you can model all situations. What are the advantages and when would you use them? It models the flow resistance of the impeller, because this is essential, as I mentioned earlier, because the delta P across the impeller can become negative. You can model pump trip and the four-quadrant operation. Disadvantages, it needs the Suter curve. And if you're a customer, we can give advice on how you can estimate the Suter curve. There are techniques for doing that. And the number of built-in Suter curves will increase. There are new sources of data for the Suter curve. We will, in the future, consider building more Suter curves into PIPENET itself. But if you do not have the Suter curve, we can help you to estimate it. The other disadvantage, you see, normally you wouldn't use the turbo pump necessarily to model pump startup, but it cannot model pump startup, and it has to be set manually. That is the disadvantage of the turbo pump. It is suitable for pump trip study, especially vacuum pressure needs to be estimated. There are applications of PIPENET where the downstream pressure can get very low. And we all know this. You can get cavitation during pump trip. But there are cases where the piping system actually can be 3.5 to 4.5 meters in diameter. They really are huge pipes. They are more like tunnels than pipes. And such large pipes are usually made of fiberglass. And fiberglass pipes, the minimum operating pressure is not even full vacuum. It can be minus 0.3 bar gauge or something like that. So see, it's very eminently suitable for cases where the pump trips, especially the vacuum pressure, needs to be estimated. Not just estimated. Of course, PIPENET is not only about calculating pressure, it is about, finding solutions to how to eliminate this vacuum. And the most common way is to add vacuum breakers. That's not the only solution. You can add a flywheel to the pump so that the pump actually trips more slowly. So you can consider the reverse flow rate in the pump, the reverse rotation of pumps, and so on. So it is useful for a very comprehensive range of applications. It's unsuitable for pump startup study where the speed is unknown. The inertial, if you want to study the startup characteristics of the pump, it's better to use the inertial pump, which we will see in just one moment. So let's go on to this and look at the turbo pump. This is a Suter curve, and these are the quantities I mentioned. They are the rated quantities, and that's all the amount of inertia, of course, doesn't depend on the speed, so it's input separately. we say that the trip is 5 seconds. The trip time doesn't mean that's the time duration of the pump spin down. That's something PIPENET will calculate. This 5 seconds is the time at which the pump trips or loses power or something. And that valve remains open just before the pressure there is 0, and the pressure there is also 0. So let's have a look at the pump itself first. The speed of the pump. You can see that it's slowing down, and during the final moments, it'll actually take quite a long time for the pump to become, absolute zero, complete stop. We look at the outlet pressure. Let's remove that. See, we need to use the same scale for them. So this is y-axis. This is something that you might find useful. So click on that. It makes the pressures, the axis for the pressure the same. So you can see that both the inlet and the outlet pressure reach the value 0. But in this, this is not a pathological case where you have reverse rotation and stuff like that. The pump speed, actually, you can see that's the axis. We'll remove those for clarity. See. Let's see there. Yeah, that's a 0 line. I succeeded this time. And you can see that it's very slowly approaching the 0 line. As a turbo pump, but because the behavior of the system here, is no different from any other, especially because this valve is constantly open. See, there are other cases I can show you. This reverse flow. It's essentially the same network. See, I've made the pressure there 5 bar. In the previous case, we had 0 bar at the inlet and outlet. Now here is 5 bar and 0 bar here. And we're using a dynamic check valve. We need to do this. In the previous case, we had what is called the non-return valve. Non-return valve will close as soon as the delta P is negative. Oh, sorry, the delta P is positive. In other words, the pressure here is higher than the pressure there. Whereas this one will take time to close. It's a time constant, and so on. Apart from that, it's virtually the same. Okay. See here again, it's unlikely that, I don't know, we'll have to look at the results, that there is actual reverse rotation of the pump, because there's a check valve here. But you could get reverse flow because that check valve doesn't close instantaneously. Yeah, it's getting towards zero, but it does not, there's no reverse rotation. But look at the flow rate. See, there is reversed flow here, I believe. Yeah. It's clearer to see if, by the way, you can move the axis to the other side as well if you wanted to. I think we do this here. Sorry, I don't want to waste time doing all that, but you see the axis position is on the right, you move to the left if you want. There are all kinds of things. I'm just showing that because you may find all this useful. Okay, so you can see that the flow rate actually goes back because the check valve is not an instantaneous closing valve. It's got a time constant. Okay, so that is the case where the flow rate, and that the flow rate is negative because this pressure here forces the flow rate through the pump. Even though the pump is rotating forwards, it's because it's so slow that the flow rate actually goes negative. When the valve closes, the negative flow stops. You can see. Let's have a look once again. It goes to zero. You can have a look at the check valve position. See, it goes to zero for a while and the flow rate becomes negative, then it opens again and finally closes. Okay? So it's all, you can see that everything makes sense. It's quite beautiful, the results that you're getting. You know, it agrees completely with what our intuition tells us. This is pump trip with reverse rotation. See, best to see case where, let's refresh that. See, the elevation of this valve is 50 meters. The pressure is the same. Of course, it doesn't have to be zero. It can be, I could have left it at 5. But in order to show that the pump actually rotates backwards, I've used quite a slow acting valve here. That is just for demonstration purposes. It starts at 10 seconds and stops at 130 seconds. The real check valve will not do that. It'll act much more quickly, usually. And so it's an exaggerated case just for illustrating the point. This time the pump trips at 10 seconds. Pressure goes 0. Pressure goes 3, 0. And that pump remains open all the time. Let's look at the turbo pump. Rotation speed. You can see, oops. Show the 0 line. See, that's 0 RPM, and you can see that it's negative. Okay, and rotates backwards for quite a bit of time. Don't forget that it will continue to rotate even after the valve is closed, because the impeller has some momentum, and that once it starts rotating backwards, it will continue to rotate backwards. That's why this hasn't gone to 0 as soon as the valve is closed. Okay. So it's beautiful, isn't it? It's amazing how the PIPENET models confirms our intuition. And also, of course, our intuition doesn't give us quantitative results, but PIPENET gives quantitative results. And of course, our intuition also may not be good enough when we have a complex network, because in a complex network, we must analyze things quantitatively. We cannot simply say, oh, I think this is what's going to happen. You know, maybe 10, 15 years ago, we had to do that because this PIPENET was in its infancy. Although the transient module has been around for 25 years, it's only about in the last 10 or 15 years that people have started actively understanding the importance of transient analysis. So there are, some other cases, and I will not show these because these are bigger examples. Well, I will emphasize this point again, that I created a lot of examples here for your benefit. They're not necessarily examples that we will have time to see today. And if you're an actual user of PIPENET, we can send you the data files. It's free. We won't sell it to you. We can send it to you free. And so please, let us know on pipenet@sunrise-sys.com. Next one. Inertial pump. I told you that there are two modes, pump trip and pump startup. We have to, for the pump trip, we need the efficiency against the flow rate. Sorry, the head against the flow rate, and the efficiency or the power against the flow rate, because efficiency, we can calculate the hydraulic power from the flow rate and the head, and so from the efficiency we can calculate the power anyway. And so we can specify that for the power. We also need to have the moment of inertia and the rated speed. They're all here. As an example, here you see there is a switch here. Using which you can select the power or the efficiency. And the power against the flow rate curve is here. And the head against the flow rate curve is here. For pump startup, we will also tick on this tab and give another curve, okay? But for pump trip, these are the only two curves we need to know. What are the advantages, disadvantages, and so on? The data is relatively easy to get. Some values may be estimated easily, and we can give you some guidance on how to estimate those values, so do contact us. Disadvantages, it ignores the resistance of the impeller. So if your aim is to study the vacuum pressure that you get when a pump loses power, which is very important in certain cases, we cannot use the inertial pump. Because if you want to, calculate the vacuum breaker size and position and so on, or a tank that you may wish to place after the pump in order to stop cavitation occurring and stuff like that, we cannot use the inertial pump. It's more limited than the turbo pump, is obvious. It's suitable to estimate the pump's spin down pattern when the pump trips. Of course, you can also change the speed using a process controller or manually. It's unsuitable for abnormal cases such as pump tripped, followed by reversed flow, reverse rotation, and things like that. It's also not suitable for pump startup scenarios. And that is this pump trip case where we're only defining these two graphs. Of course, inertial pump can calculate the startup scenario, but you will need to give a little bit more data for that. That is the next case we'll consider. These are some results. The behavior with the long pipe and short pipe is studied here. I will just take one, the short pipe. The chance will run more quickly. So the pipe, you can see it's 10 meters long. Pressure there is 0. Pressure there is 0. And let's have a look to see what you've specified in the library. See, because it's a pump trip, see, this is what I said. You can select the efficiency or the power, and that's this graph here. And the pump performance curve is the usual pump performance curve. It's the same. That's the way you define the pump curve with a simple pump. Okay. What about the information node? How do we tell the pump PIPENET that the pump is going to trip? See, we use the step profile because we cannot tell PIPENET how the pump is going to slow down, spin down, because that is what we want PIPENET to calculate. So the speed is 1, which, as you know, is a design speed or the rated speed. At 5 seconds, we say that the input goes to 0, because that is not the speed of the initial pump. That's when the signal goes to 0. So let's look at pump speed. See, the setting of the inertial pump is what you supply to the information node. And if you look at that, that's a step function that I input. But that is not the speed of the inertial pump, because the inertial pump will spin down, and that is what we're calculating here. Okay, that's the inertial pump in the trip mode. Let's go here. inertial pump in the startup mode. As I said, there are two modes. You can actually, let's stop all these things. See that in the library. See? There are two modes. Trip, startup, or both. Essentially, the startup mode is the same as both, but they're separated just to avoid confusion. And if you have the startup mode, let me open the startup data file and then it'll be clearer. We take that one there. The inertial pump. This is a curve we looked at, but this tab, see, that's the relative speed, which goes up to 1, as you know, and the torque. So the speed torque curve for the pump. We need to input that. If we open the other case, see, there's nothing there. Okay. Whereas with this case, where we are studying the pump startup, this is with a step function. So here, it's the opposite. It stays at 0 and 5 seconds. You know, it's a step function because it's like pressing the button to start the pump. It's an instantaneous action. And that's why we use the step function. But of course, the rotation speed of the inertial pump is not a step function. Okay? So that's how the pump starts. I mean, it takes, you know, approximately, let's say, 5 seconds to run up, which is what you would expect. Okay, so this is using the inertial pump in the startup mode. The two differences, or three differences if you like. We choose a startup mode here. We have to supply the torque curve because how the pump runs up depends on the torque. And that's the torque against the speed. And then we specify through the information node the time at which you press the button, essentially. Of course, it could be a switch or something like that. It doesn't matter. For example, if there was a control system which is sensing a pressure somewhere else, and another pump fails, you can use the control system to start this inertial pump. And then it'll be a switch. In the control, these are control components. We will look at the control loops in another webinar in the future. PIPENET has very sophisticated control systems modeling capability, which is very essential in many cases. So let's run this. Actually, let me just check because I can't remember. Yep. Okay. The inertial pump, we're interested in the speed of the pump. Oh, we've already done this. That's the step function that we input. Okay, so that's the inertial pump in the startup mode. In all these things, one question which might be going through your mind is, how do the three pumps perform when they should perform in the same manner? For example, we know that the inertial pump cannot model the vacuum pressure downstream and stuff like that, because it cannot model the delta P across the impeller. But on the other hand, if your model is supposed to work the same way with all three models, the results should be the same. That's what this is about. Let's just pick one case. See what we're considering here. We are considering a case where the pump essentially, stops at 10 seconds. And it takes 15 seconds to spin down. And then at 50 seconds, it starts up again, and it ends up at 50% of the rated speed. Now, this doesn't actually consider any of the dynamics of the pumps themselves, like the impeller speed of rotation to be calculated and stuff like that. I'm inputting all those things. I'm doing the same for all three of them. These valves are here simply to create one network. You see, they're both closed. So the pumps actually work independently. It's only to create a single network. We've got these valves and they're closed. Just to be sure, the pressure is 0. The pipes are the same. The inlet pressures are the same. And we saw that the specifications for the pump speed is also the same. And if the models are good enough, I should get the same results with all three models. Because that's a question that might be going through your mind. Will they produce completely different results? We can, for example, let's compare the flow rates. See, it's a very small difference. But it's, seeing that the models work quite differently, because don't forget, for the turbo pump model, we didn't supply the pump performance curve at all. whereas for the inertial pump and the simple pump, we supplied the pump performance curve. So this, the turbo pump, the pump performance curve, was calculated quite differently. So you would expect some differences. So you can see that. Pressure. The same, very slightly different, but they all have the same pattern. So this is about pumps. I've said virtually everything I want to say. There are, if you don't mind, I'll just take, there are some examples here. We'll just take this. It's a real example. This is a cargo tank of an FPSO. I thought it might be interesting for you to look at this because many of the FPSOs are built in Asia, and since this might be interesting for you. And this is a shuttle tanker. Well, of course, it could be a pipeline. There's a hose here. And, the standard case is when that shuttle tanker is fully loaded, is to close this valve. And the other valves all remain open. So see, let's look at the text output. See, that's the maximum pressure. In fact, if we go see in the hose, the maximum pressure is 35, which is too high. So, see, BP, this is a BP. I don't know who the actual operator is, but it's a BP facility. It came up with a very, very simple idea. This goes 3 valves rather than just 1 valve. See, the idea is that if we just close the 1 valve, it bears the brunt of the flow rate going. If you close 2 other valves, the inlet flow or the inlet pressure coming to this valve is already decreased by the other valves closing. It's a very, very simple approach. See the maximum going right down. The hose is within its rated pressure. It's very, very simple solution. And of course, the beauty of this is that we may think intuitively that this is a good idea, but PIPENET is what tells you quantitatively that your idea is correct. I will close now. And as I said, I created many examples here, which I knew I wouldn't be able to show today because they're all will take too much time. I mean, this is what 17 files just under forces, no, not just 17 files, 17 cases, and some of them have multiple cases, and so it would have taken too long. So if you already have PIPENET and you want to have the data files, we can send them to you. But if you're not if you don't have PIPENET, we can still send you the Word documents which are used for the presentation. Thank you very much for listening to me. As always, it's a great pleasure to be here And we appreciate the fact very much that you've given up your time. Time is the most precious things we have, apart from, of course, other human beings that were important to us. But, you know, so you've given up your time to be here. Thank you very much. We appreciate it very much. We look forward to being of further service to you. Thank you very much. Victoria?
And Dr. Sebastian, thank you very much for delivering this session. I hope it was useful and interesting to all the attendees. And I would like to confirm that we will share the video recording of this webinar slightly later today or tomorrow. And also, if you would like to receive a certificate of attendance, please write to me and we will be happy to provide the certificate upon request. I hope all your questions in the chat have been answered. Chelvi, I believe you were responsible for answering the questions. Could you please tell us if you managed to answer all the questions?
Yeah, yes, Victoria, it's all clear, and some of them will write to pipenet@sunrise-sys.com for interior and extensive details. No issues, it's done.
Okay, thank you very much. Okay, great. So I would like to repeat that if you have any questions left that were unanswered during the webinar, please send your questions to the email address which you see now on your screens, pipenet@sunrise-sys.com, and we will be happy to answer your questions. Now this session is over. I would like to thank you all for attending it, and I would like to confirm that we are planning many more sessions this year. Please follow our announcements and our invitations, and we look forward to seeing you online in the future. Have a good evening, good day, and thank you. Bye-bye.
Well, I would also like to thank Victoria for organizing this webinar. Thank you, Victoria. And I would like to tell the others, like Chelvi and Legend and Luke and Shalika, who have been here. And thank you very much indeed. And we appreciate all your work, and all of us work together. We have a common purpose of users and the support team. We all have a common purpose. Thank you very much indeed. Bye-bye.